Imagine what would happen if none of our houses had their own unique addresses. How would we contact each other, meet each other, or talk to each other? Luckily, we do happen to have a well-established system of assigned addresses, which makes locating people very easy. Does the chemical world, with its infinite atoms and subatomic particles, have a similar system? Let's find out. Welcome to our show on electronic configurations. Today, we will learn how electrons are arranged in an atom according to rules like the Aufbau principle, Pauli's exclusion principle, and Hund's rule. We'll also learn how to write the electronic configuration of various atoms and discuss the reasons for their stability. And finally, we'll take an in-depth look at probable exam questions. Let's begin with a riddle. What do you have in common with Einstein, Max Planck, Heisenberg, and Niels Bohr? Well, for today, you are going to be a student of quantum mechanics just like they were. You already know that a positively charged nucleus forms the dense core of an atom. This nucleus is surrounded by definite paths called orbits or shells in which an electron moves. Circling the nucleus are electrons, which occupy regions of electron cloud called orbitals or subshells. Orbitals are where the probability of finding an electron is the highest, say 99%. If you have paid attention when I was teaching you the periodic table, you would remember the terms S, P, D and F, which denote the types of orbitals in an atom. Here is a closer look at the shapes of S, P and D orbitals, which are based on the electron cloud formed by them. They are spherical, dumbbell and double dumbbell shaped respectively. We know that each atom has a different number of electrons. So how do we locate these electrons for various atoms? And is there a way to denote their location? Yes, there is, and it's called electronic configuration. The electronic configuration of an atom is a form of notation which shows how the electrons are distributed among the various orbitals. In order to assign a configuration to an atom, one must follow certain rules. First, you must know the maximum number of electrons a shell or orbit can carry. This is given by the formula 2n squared, where n is the shell number. Replacing the value of n for each successive shell, we get the following. The first orbit or K shell has a maximum of 2 electrons. The second orbit or L shell has a maximum of 8 electrons. For the third orbit or M shell, the maximum number of electrons is 18. The fourth orbit or N shell will have maximum 32 electrons. You now know the maximum number of electrons a shell or orbit can have. But what about orbitals? Here is how the orbitals are denoted in increasing order of their energy levels. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p and so on. And now let's understand the rules by which electrons fill orbitals. Keep in mind that a significant number of exam questions are related to this topic. Some of you may get confused by the huge number of orbitals, especially as atoms get larger in size. So let me tell you about the Aufbau principle. This principle states that the lower energy orbitals are first to get filled. Only once this happens can the higher energy orbitals be occupied. Energy levels of orbitals are determined by the n plus L rule. This states that the orbitals with lower value of the n plus L are filled first. Do take note that n is the principal quantum number and L is the azimuthal quantum number. The Aufbau principle states the order in which orbitals are filled. But how many electrons can an orbital occupy? This was a question which led the leading German physicist Wolfgang Pauli to propound one of the central theories of quantum mechanics. According to Pauli's exclusion principle, only two electrons may exist in the same orbital, and these electrons must have opposite spins. What does this mean? Let me give you an analogy. Imagine yourself seated in your designated chair in the classroom. Now, if I said that there was another student with the same name, appearance, and behavior as you, sitting in the same chair at the same time as you, wouldn't you think it was illogical? Wouldn't you say, but Debu, that person has to be me? It's exactly this absurdity that Pauli uncovered. Let's take the case of electrons belonging to the 2s orbital. Both electrons have the same principal quantum number, that is, n is equal to 2. They also have the same azimuthal quantum number, that is, L is equal to 0, and the same magnetic quantum number, that is, ML is equal to 0. So if the same set of quantum numbers applies to both electrons, it indicates that they are identical in location but different in behavior. This was the contradiction that Pauli resolved. He realized that there must be another parameter by which electrons are identified and configured. He proposed a fourth quantum number, ms, known as electron spin quantum number. This is used to describe the spin of an electron either clockwise or counterclockwise. In English, the synonym of quantum is amount. And right now, I'll allot myself a break and you the task of answering a question. What does Aufbau in Aufbau principle mean? Keep thinking. Welcome back to our discussion on electronic configurations. Before the break, I had asked, what does the term Aufbau in Aufbau principle imply? Aufbau is a German word that literally means building up. And as we just learned, there is a progression of building up in the number of electrons that are filled from lower energy levels to higher energy levels. I hope this bit of trivia would help you recall the Aufbau principle if it is asked in your exams. Using the rules mentioned earlier, we learned how to fill the orbitals. But the manner in which they are filled is also important. This is based on Hund's rule given by German physicist Friedrich Hund. According to it, the pairing of electrons in orbitals belonging to the same subshell does not take place until each orbital belonging to that subshell has got one electron each. If we take the case of p orbital, px, py and pz must all be singly occupied before the next electron can be filled in. So, the correct order of electrons filling the 2p subshell is as shown. You must be wondering about this new diagram representing orbitals. This is called an orbital diagram, where each orbital is represented by a box and the electron is represented either by an upward half arrow implying positive spin or a downward half arrow implying negative spin. Now, isn't this an easy way to approach tricky configuration problems in the exams? Now let's see how we can apply the rules that we have just learned. Let's take the example of a helium atom in which both electrons occupy the 1s orbital and therefore have opposite spins. We denote helium with a 1s2 electronic configuration. This gives us the following information. 1 represents the shell number or principal quantum number n. S represents the azimuthal quantum number L, which indicates the subshell. Exponent 2 refers to the total number of electrons in that subshell. Remember, I was talking of assigning addresses to electrons at the beginning of the show? Well, this is how it's done. Can you now do the same for atoms of other elements? Let's look at the electronic configurations for beryllium, carbon, and sodium. They each have the atomic numbers 4, 6, and 11 respectively. The orbital picture notation clearly shows that the last electron enters in 2s, 2p, and 3s respectively. Take a look at the electronic configuration for sodium. 1s2, 2s2, 2p6, 3s1. Sounds a bit intimidating, doesn't it? Fortunately, there is a shorter way to represent it. You can replace the first three configurations with the chemical symbol of the noble gas they denote, which in this case is neon. So an alternate way to write the electronic configuration for sodium is parenthesis neon 3s1. Often, examiners may ask you to use this notation rather than the long forms. So be sure to brush up on the configurations of noble gases. Most elements follow the rules of configuration we have discussed so far, but there are some exceptions. Let's take a look at two such examples, chromium and copper. Chromium has an atomic number of 24 and the expected configuration would be parenthesis argon 3d4 4s2 as per the rules of filling orbitals. However, the actual configuration is parenthesis argon 3d5 4s1. For copper with atomic number 29, the expected configuration as per the rules of orbital filling is parenthesis argon 3d9 4s2, but in actuality it shows a configuration of parenthesis argon 3d10 4s1. In each case, the electron has entered a higher energy orbital. That is, instead of 4s, it has moved to the 3d orbital. This is a violation of the Aufbau's principle because, according to it, 4s should be filled first. Further, in chromium, the 3d orbital is half-filled. Time now to solve a query that a young friend of mine has.
While I know what the electronic configurations of chromium and copper are, I don't know why these configurations are obtained in violation of Aufbau's rule. Can you please explain why this happens?
That's a good question, because if I were your examiner, I would ask that question too. The electronic configurations of copper and chromium violate the Aufbau principle in the interest of stability. When 3d is filled before 4s, the half-filled 3d orbital of chromium and the fully filled 3d orbital of copper attain a more symmetrical distribution of electrons, leading to the increased stability of the atom. Another reason why some atoms show unexpected stable configurations is because of exchange energy. In degenerate orbitals, that is orbitals with the same energy, Electrons have the tendency to exchange their positions with each other, and this releases energy known as exchange energy. The greater the number of exchanges, the greater is the exchange energy, and greater is the stability of an atom because systems at lower energy are more stable. It is important for you to know that half and fully filled orbital configurations like D5 and D10 enable greater number of possible exchanges as opposed to, say, a D4 and D9 configuration. In a D5 configuration, the electron in the first orbital can exchange its position with electrons in second, third, fourth, and fifth orbital. Similarly, the second electron can have three types of exchanges. The third electron, two types of exchanges, and the fourth electron, only one exchange. I'm heading for a short break now, but when I return, get ready to jump to a higher energy level with exam decoded. Welcome back. Over the course of this episode, we have learned the rules that govern the arrangement of electrons in atoms. Let's go over the main points once more before we proceed. We are now familiar with Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. We have also learned about the exceptional electronic configuration of copper and chromium and the reasons for their stability. Now that we are fortified with the facts, let's move on to exam decoded. Welcome to exam decoded, where I will give you the ideal configuration to crack your exams. You know, answering exam questions doesn't always have to be stressful. It can also be an invigorating challenge, a lot like our rapid fire round. Let's go over the rules. This round has 5 questions for 1 mark each. You will get not more than 5 seconds for each answer. Track your scores carefully and I will tell you what they mean. Your first question is, what is the maximum number of electrons that can be accommodated in a p subshell? A, 6, B, 5, C, 7, D, 4. If you have been watching the show carefully, you will know the answer is A, 6. Next question. Complete the following. Atomic orbitals are filled according to A, Pauli's exclusion principle, B, Hund's rule, C, Aufbau principle, D, all the 3. The correct answer is D. All the 3 are rules for how electrons are filled in orbitals. Your third question is, which of the following subshells can accept a maximum of 10 electrons? A, 2p, B, 4f, C, 3d, D, 3s. The correct answer is C, 3d. Your fourth question is, which of the following orbitals are degenerate in a multi-electron atom? A, 3d subshell, B, 3s, 3p and 3d subshell, C, 1s and 2s subshell, D, 2d subshell. This is a slightly difficult question and the correct answer is A, 3d subshell, because the 3d orbital has 5 degenerate orbitals and the 2d subshell cannot exist. Your last question is an easy one. Answer true or false. 2s orbital is lower in energy than 2p orbital. The correct answer is true. Time now to see how you have fared. If you have got all 5 answers right, then you are a high flyer and this is definitely your strong subject. If you have scored 4 or 3, then you are an achiever. You are doing very well, but a bit more practice is needed. If you have scored less than 3, then you are a learner who must keep studying hard to master this topic. But no matter how you did in our rapid fire round, do log on to www.topperlearning.com for many more tests and question papers. It is important to know that the topic electronic configuration of atoms carries a weightage of 6 marks, making it a critical part of your exam paper. From this topic, you are most likely to get very short answer type questions for 1 and short answer type questions for 2 or 3 marks. These questions will test your knowledge ability and you could be asked to explain the different rules of electronic configuration or justify configuration of different atoms. Let's take a look at one such question for 3 marks. It's a tricky one, so I will lead you through the various steps. Write the electronic configuration for beryllium, iron 2+ and sulfur 2-. To derive the electronic configurations, you need to first know the atomic number or value of Z. For beryllium, Be, atomic number Z is 4. So, the total number of electrons is 4. Since it is in ground state, the electronic configuration is written for Be as parenthesis helium 2s2. Similarly for iron, the atomic number Z is 26. Now you must remember that we need the configuration for an iron ion, which has lost 2 electrons from its outermost shell. So, the electronic configuration of Fe2+ is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. In short form, it is parenthesis argon 3d6. Finally, let's write the configuration for sulfur, where the value of Z is 16 and configuration in ground state is 1s2, 2s2, 2p6, 3s2, 3p4. For S2- ion, 2 electrons need to be added to the next highest partially filled shell. Using the Aufbau principle, we fill orbitals of lower energy first and get the configuration as 1s2, 2s2, 2p6, 3s2, 3p6. Each configuration will fetch you 1 mark, bringing the total to 3 marks. In questions like these, be very particular about noticing if the element is in its atomic or ionic state. It's time now to join our expert who has more tips like this.
As discussed about the electronic configuration, the exceptions for the chromium and copper is due to the extra stability of half-filled and completely filled orbitals.
One of the foremost quantum theorists, Niels Bohr, once said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." While I do hope today's show has not shocked you, it has made you appreciate the incredible world of subatomic particles and brought you one step closer to understanding its concepts.